Sketch the domain structure you would expect in spherical samples of ferromagnetic materials with the following properties. First, zero magnetocrystalline anisotropy. Second, large uniaxial anisotropy. Third, large magnetostriction. And finally, a very small sample. So what happens if we have zero magnetocrystalline anisotropy? There is no preferred direction for the magnetization to point, and in order to minimize the magnetostatic energy, we're going to have this vortex structure forming. So the energy to consider here is the magnetostatic energy. So to minimize magnetostatic energy, a vortex structure forms. And why do we have a vortex structure minimizing magnetostatic energy? As you can see, we have no free poles here, north and south poles. They're all paired. Therefore, we don't have a Dirac field forming in the structure. So the Dirac energy or magnetostatic energy is zero. So this configuration, this is energetically favorable because it yields zero demagnetizing field. Okay. Now part B, large uniaxial anisotropy. So let's say that this is our easy axis. So we have large uniaxial, and that one axis is this axis. Basically, this will force the magnetization to point along the easy axis. So in order to minimize anisotropy energy, we must have magnetization pointing along the easy axis. So to minimize anisotropy energy, magnetization must lie along the easy axis, and it's not single domain, it's forming several domains here. You can see this is basically to minimize the magnetostatic energy. So overall we have this north-south pairs forming along the edges of the specimen. So to minimize magnetostatic energy, it must break into domains. So it breaks into domains. Now, how many domains will form? So that's an important question. Now, every time we form a domain here, you can see that you have these domain walls where the magnetization is not pointing along the easy axis, and therefore this is going to cost some energy. So to minimize the domain wall energy, few domains will form. So the number of domains is limited by the domain wall energy. So to minimize domain wall energy, few domains will form. Okay. Now part C, we have large magnetostriction. Now again, we have anisotropy in the system when we have large magnetostriction. And in this case, we must have closure domains forming in order to minimize the magnetoelastic energy. So we still have the main domains having magnetization points along easy axis. And let's say that we have cubic anisotropy, assuming cubic anisotropy and 90-degree domain walls form to minimize magnetostatic energy so you can see here we have 90-degree domain walls here, and these domains will basically accomplish flux closure. So to minimize magnetoelastic energy, small flux closure domains form. All right. Now, when we have a small sample in part D, if this is a small spherical ferromagnetic material, the dimensions of the sample are less than the domain wall width. What we see is that it costs too much energy to form a domain wall, and therefore we must have a single domain. So the sample in this case is so small that the domain wall energy will be too high in other words, the dimensions of the sample are less than the domain wall width. Now there is another extreme case here. The sample is very small. It's extremely small. In that case, we may even lose our thermal stability, and the magnetization can point in any direction. So if even smaller, the sample becomes super paramagnetic. Okay, so that means the anisotropy energy, the anisotropy constant, uniaxial anisotropy constant times the volume now becomes comparable to thermal energy, leading to random alignment for magnetization. So random magnetization will result. Okay, so to summarize, we have analyzed the cases, 4 different cases for spherical samples of ferromagnetic material. If it has no anisotropy, it's going to form a vortex structure to minimize magnetostatic energy. If it has a large uniaxial anisotropy, the magnetization must point in the direction specified by the uniaxial anisotropy, but we must form domains to also minimize magnetostatic energy. However, the number of domains we form will depend on the energy cost in forming these domain walls. So few domains will form. If we have large magnetostriction, in addition to these requirements, we must form closure domains in order to minimize magnetoelastic energy. And for very small samples, the sample dimensions become less than the domain wall width. The energy cost in forming a domain wall is too high, so it becomes single domain. If the sample is really small, then we can have the anisotropy energy, KUV, becoming comparable to thermal energy, which means that the anisotropy requirement is no longer present and magnetization can point in any direction, making the sample super paramagnetic.